Okay, so let's try our first example with plugging in some actual numbers and see how we solve an equilibrium problem based on what we know about the equilibrium condition, which is that at equilibrium, this particular product of the numbers of each molecule raised to their stoichiometric coefficient is equal to the product of the partition functions raised to their stoichiometric coefficients. And in particular, this term on the right side, product of the equilibrium, the partition functions, we call that the equilibrium constant, which we can write as KEQ, or sometimes we just write it as K. The quantity on the left-hand side, we call this the reaction quotient. We'll have more to say about that in a future lecture. The important thing to understand for right now is the term on the right, the equilibrium constant, is a constant that has a particular value at any given temperature for any given reaction. The quantity on the left, the number of molecules, as the reaction proceeds forwards or backwards, we consume molecules of reactant and produce molecules of product if the reaction is going forward. So this quantity on the right, the number of molecules, is always changing as the reaction proceeds. So what that means is the quantity on the left, this reaction quotient, is exactly equal to the quantity on the right, the equilibrium constant, only at one particular value of the extent of reaction. So that is what lets us solve for how far the reaction proceeds when it reaches equilibrium. So as an example, we can consider this, our favorite example so far, of H2 and Br2 reacting to form HBr. So let's suppose that we know, or we've looked up, or we've measured experimentally that the reaction, the equilibrium constant, has a value of 1800 at some particular temperature that we're interested in. And at that temperature, we introduce 1.5 moles of H2, same amount of Br2, same amount of HBr into a reaction vessel. So the initial amounts of each component are all exactly 1.5 moles. We could do that, for example, since they're gases, by introducing gases at the same partial pressures of each gas into a vessel at a pressure and volume and temperature that works out to be 1.5 moles of each species. The question then is how much of each species is present once the reaction reaches equilibrium. The reaction will either shift forwards or backwards, consuming H2 and Br2 or consuming HBr, until it reaches equilibrium, and we'd like to know how much of each species there is at equilibrium. So the first thing we know is, even though we don't know how far the reaction will go, we don't know the value of squiggle, the extent of reaction, but we know that however much the reaction proceeds, if the reaction proceeds to an extent squiggle, then the number of moles of H2 will be the initial amount, 1.5 moles, minus that number of moles of extent of reaction, because the stoichiometric coefficient tells us 1 mole of H2 is consumed every time the reaction goes 1 mole of times. Likewise, for Br2, initial amount 1.5 moles minus the extent of reaction. But for HBr, since it's on the product side and 2 moles are produced, the amount of HBr, as when the reaction has proceeded to some extent squiggle, is 1.5 moles plus 2 times squiggle. So that tells us how much of each component there is. The equilibrium condition, the reaction quotient, the product of number of moles of each species raised to the stoichiometric coefficient, that ends up looking like products divided by reactants, because the reactants have a negative stoichiometric coefficient. So this ratio, molecules of HBr squared over molecules of H2, molecules of Br2, that reaction quotient has to be equal to K. If we then take each of these terms that we've determined and plug them into the reaction coefficient, or the reaction quotient, sorry, moles of HBr is 1.5 plus 2 squiggle. In the denominator, moles of H2 and Br2 is 1.5 minus squiggle for each one of those. So that ratio has to equal K. So now we have one equation and one unknown. We know the value of K. We're trying to find squiggle. Ordinarily, for this reaction, that would be a quadratic equation, but so that we don't get too bogged down in the algebra, I've set it up so that the quantity in the denominator is a perfect square. The quantity in the numerator is also a perfect square. So if I take the square root of both sides of this equation, so in this step all I've done is take the square root. So what we end up with is 1.5 moles plus twice the extent of reaction divided by 1.5 moles minus the extent of reaction must be the square root of the equilibrium constant. Now we just have a little bit of algebra to go. take the denominator of this expression and move it over to the right-hand side, and we get the equation here, 1.5 moles plus twice squiggle is equal to the square root of K times 1.5 moles minus squiggle. If I distribute those terms and collect all the terms involving squiggle over on the left-hand side, there's a 2 squiggle from here, and there's a minus square root of K squiggle from the right-hand side, which I move over to the left-hand side. Likewise, the terms that don't involve squiggle, there's a 1.5 moles times 1 on the left, and a 1.5 moles times root K on the right. And if I do the algebra correctly, I see that that's 1.5 moles times root K minus 1 on the right. Then just divide through by root K over 2, root K plus 2, and we find that squiggle is this quantity, 1.5 moles times root K minus 1 over root K plus 2. Now if I insert the value of K, 1800 for the equilibrium constant, and plug those numbers into a calculator, what I find is that the total, the result, the net amount of each, the extent of reaction, the amount by which the reaction has proceeded, is equal to 1.4 moles. We don't want to know the extent of reaction, we want to know how much of each component remains after that much reaction has proceeded. Number of molecules of H2 and Br2 is the initial amount, 1.5 moles. I should have written moles here. Minus squiggle, so 1.5 minus 1.4 is 0.1 moles. HBr, I've got 1.5 moles plus twice the extent of reaction. So if I add twice 1.4, that's a total of 4.3 moles. So this is the answer to the question we asked initially. After the reaction proceeds, H2 and Br2 will be mostly consumed, leaving us with only 1/10 of a mole of each. There's a significant amount more of HBr. The 1.5 moles we originally had has grown to 4.3 moles. We can double check and make sure that our answer is right, make sure we haven't made a mistake in the algebra anywhere. So if we plug those final results back into the reaction quotient, 4.3 moles squared in the numerator divided by 0.1 moles for H2, 0.1 moles for Br2. If I divide those quantities, what I find is 1800. So that does confirm that the answer we arrived at does indeed reproduce the equilibrium constant. So every example is a little bit different. The algebra problem we had to solve in this particular case had the 2's in it and the squareds in it in the places they were because of the stoichiometry of this reaction, 1 plus 1 becoming 2 moles of something else. Every individual reaction is a little bit different and leads to a slightly different problem, but the key is always just to set up the reaction quotient being equal to the equilibrium constant and then solve for the extent of the reaction that allows those two things to be equal to each other.